All right, well, we have a review problem first then, number 1 at 3.3.3. Which says that a 2 kilogram mass hangs from a spring with a Hooke's law constant K equals 8 and is attached to a driving force. There's some constant F0 times sine omega 0 t, omega 0 being the frequency at which it's driving. So it's a sinusoidal oscillation pushing it, such as you might get in an electronic circuit or something if you apply the voltage to get alternating current. Show that the driving angular frequency, only the driving angular frequency, omega equals 2, will cause resonance. If you call it omega 0 equals 2, will cause resonance, and find the general solution for the motion when omega 0 equals 2 and S 0 equals 8. So, what we have then is the basic equation says d squared u dt squared plus c du dt plus ku equals the driving force, which is F0 sine omega 0 t. You can just memorize this actually once you get used to it. What this says, the force is equal to, this with a minus on the other side, is the force due to the dashpot damper if you have one. This one with a minus on the other side is the spring force, and then this is an externally applied force that you push the mass with. And the idea is that resonance occurs when the angular frequency here of the applied force omega 0 is equal to the natural spring of the system without the force. So what we'll do is we'll solve the homogeneous problem, UH double prime. And we've got to put in the letters here too. It's a 2 kilogram mass and a constant K equals 8. So we'll say, I forgot my M here. So we've got 2 U double prime, if I put in M equals 2. And the idea is that this one has no damping. So this term is gone. It's 0 du dt. Plus K is 8 U equals F0. Let's leave that off. Sine omega 0 t for this problem. And then to see what causes resonance, we'll say you can look at the associated homogeneous problem. By dropping the force that's applied on the right-hand side and just putting 0. So it's 2U double prime plus 8U equals 0 is the homogeneous problem. So I'll put a little H indicating I'm solving the associated homogeneous problem. There it is. Now we know how to solve this. We can divide through by 2 just to simplify and say it's, well, UH double prime plus 4UH equals 0, which has then the characteristic equation, replacing U double prime with R squared and U with 4, R squared plus 4 equals 0. Tells you that you have two solutions, R1 and R2, are plus or minus 2I. That indicates that the general solution is UH equals an arbitrary constant C1 times cosine 2t plus an arbitrary constant T2, C2 times sine 2t, right? The two coming from here. Independent solutions are e to the 0, if you think of this as 0 plus or minus 2I, times cosine 2t and e to the 0 sine 2t, which is just cosine 2t and sine 2t for these pure imaginary solutions to the characteristic equation. So we have this solution to the homogeneous problem. This is now the angular frequency at which the the system without a driving force would oscillate. If you pull the spring back and let the thing go without this additional driving force, F0 sine omega 0t, then it will oscillate with an angular frequency too. You can also write this as a single sine function. Now, the second step in solving a second order linear equation with constant coefficients is to try and find a particular solution. Since the right-hand side comes out of the table, after all, it's a sine function, there's a particular solution of the form UP equals some other constant. We could call it gamma 0 or whatever letter we like, times cosine omega 0t plus some constant delta 0 times sine omega 0t. And so that's the form of a particular solution according to the table, provided what?
It's not a solution to the homogeneous.
Yeah, provided neither term here is a solution to the homogeneous problem. Well, it's a solution to the homogeneous problem if and only if omega 0 equals 2. So this is for omega 0 not equal to 2. But if omega 0 equals 2, then you have to multiply by t, and then you get t times gamma 0 cosine omega 0t plus delta 0 sine omega 0t. And actually, in this particular problem, you can, in fact, leave out the cosine term. It's kind of hard to see except by experience. We said in general, you need both the sine and cosine. I made that point clear. If you have the driving force on the right-hand side as a sine or a cosine, and generally need both of these. However, in the special case that you don't have the first derivative here, which we don't here, there's no damping term, right? If you don't have a first derivative, then you can just choose, if this is a sine, you choose this to be a sine. If this is a cosine, you choose this to be a cosine. Because think about it. If you put sine in here, second derivative of sine is sine minus the sine times the number. And this is a sine here, and you can make this equal to 0 to solve the homogeneous problem. If you want to get sine here, you can plug in just the sine term, and the second derivative will be sine, and the 0th derivative will be sine, and so you get a sine. So actually, in this particular problem, we leave out the cosine because it's going to turn out that gamma 0 equals 0 when the first derivative isn't here. In other words, we're plugging it into this equation here in order to get a sine. This equation here, in order to get a sine, we use sine here, and the cosine here and cosine here contribute only to cosine on this side. They don't match the right-hand side, so their coefficient has to be 0. Okay, so the particular solutions of this form or of this form. And what happens then is this shows that if omega 0 equals 2 in the driving force, if you drive it at the natural frequency, 2 radians per second of the angular frequency here, then you'll need a solution of the form t times the sine function. So it'll be this case that we did before where you have the 2 lines and the particular solution oscillates like that and grows. But if omega 0 is not equal to 2, the homogeneous natural frequency, then the particular solution will just be a sine wave, a steady amplitude. So that establishes it right there. So resonance multiplication by t in the particular solution occurs only in the latter case. Omega 0, the driving frequency equals 2. That's part A, we should call this A. Now on part B, it says if omega 0 equals 1 and F 0 equals -6, find the general solution. This is not resonance, right? Because omega 0 is not 2. Now, part B is if F0 sine omega 0t, the right-hand side is actually -6 sine 1t. What is the solution? Well, we have this differential statement. Oh, I'm erasing all my stuff I set up, don't it? Okay. We have that u double prime, 2u double prime plus 8u equals -6 sine t is the differential equation. Maybe I'll just erase this. I'll rewrite it just so we can finish our problem. Yeah. And in this case, the homogeneous solution we already found is C1 cosine 2t plus C2 sine 2t. All we did was change the driving function, sometimes called, the right side is called a forcing function. That is, you're applying a force to the mass on the it's external. So the forcing function. So that's step one, and then step two is u particular, according to our prescription there, has to be a number, delta 0 times sine 1t, right? If the right-hand side is a constant times sine, then the corresponding particular solution by undetermined coefficients is a constant times sine plus a constant times cosine. And we said in the particular case that the first derivative isn't appearing in the equation, and it isn't here, then we just use the sine because the cosines will follow it anyway. So we'll seek a particular solution to this form by undetermined coefficients. In the special case, with b equals 0, the coefficient of u prime is 0. So we plug that in. We need the first derivative is delta 0 cosine t, and the second derivative is minus delta 0 sine t. And when you plug it in to the differential equation that we have, which was this now, this is part B, is to solve this equation. We get with 2 times second derivative is minus delta 0 sine t plus 8 times the function itself is delta 0 sine t has to equal the right-hand side minus 6 sine t. And so what does it say? It says 6 delta 0 sine t equals minus 6 sine t. Tells you that delta 0 equals -1, right? Method of undetermined coefficients. You plug in the form of the solution with the coefficient undetermined and determine the coefficient is -1. And so I get then that UP, particular solution, is -1 times sine t. So there's a particular solution. I guess I'll erase one more thing here. Shouldn't have put this up, I guess. Step 3 is to say that the general solution is U equals the homogeneous general solution plus any particular solution. So it must be C1 cosine 2t plus C2 sine 2t plus -1 sine t. So minus sine t. There it is. There's part B, the solution. When you force it with this driving forcing function of -6 sine t. So this solution, when the driving force is sinusoidal, not at the same frequency as the natural resonant frequency for the function, is the sum of 2 sine waves. This can be written as a sine wave of angular frequency 2. This can be written as a sine wave of angular frequency 1. So the period of this is 2 pi over frequency is pi, and the period of this one is 2 pi. And so what you have is you're adding a wave of period 2 pi and a wave of a different amplitude of period pi that oscillates twice as fast. Let's see, can I do that? Here's one here, I guess about like that. And when you add these two together, you get some sort of combined solution that oscillates around this one, the bigger one, if you like. So if you try to sketch this, here's the homogeneous solution, here's the particular solution. And the solution U of T looks something like that. Okay. So that was one of the cases. Well, first thing I wanted to do today, let me go back and review just a little bit, was summarize all this, because this all is so much that it's easy to just, when it becomes a jumble, it's easy to forget. So let me go back to page 100 here where I have this, and let's see if I can find the summary again. A couple of you asked me about this after class last time, and I just ran out of time. I wanted to put this up. This clears it. That's the right bit. It's not it. There we go. Oh, no, it's before that, I guess. Here we are. So this is the summary of all the different results you can have from your damped driven oscillator. Put a mass in a spring and possibly damp it and possibly push it with an external force. With no damping and no external force, you get simple harmonic motion, sinusoidal motion, right? If you damp it with a dashpot damper, resistance proportional to velocity, such as here's an example here where C equals 2, right? This is with C equals 0. Then you can get, this is the underdamped case. You can get overdamped, critically damped, or underdamped, and the thing decays exponentially to 0, right? Because the damping gradually reduces the motion until it's nothing. In the underdamping case, the mass swishes back and forth across its equilibrium position, like the GIF we showed the other day. So there's underdamped. Here's critically damped, it just decays exponentially. Here's overdamped, and it decays slowly exponentially. Now, if you have no damping, but you do drive it. So right here's no damping, no driving. These three are with damped and no driving. This one is driving and not damped. So here's no U prime term, no damping, but there is a driving force over here, minus 10, a forcing term, if you like, minus 10 cosine AT. And what you see is you get a sum of sine waves like the problem we just did. You have a homogeneous solution, maybe that looks like this. And then you're adding on top of it a little particular solution that's also a sine wave of a different frequency. And between them, you get oscillation about the larger amplitude sine wave by the smaller amplitude sine wave. And so you get some behavior like that. Now, however, the other case we mentioned over there in part A was if you get resonance, then you have T times a sine wave in the particular solution. And the particular solution goes like this between two lines, oscillates back and forth, while the homogeneous solution just oscillates in a sine wave. And the general solution is the sum of a sine wave and a sine wave times T, right? Homogeneous solution and the particular solution. So initially, you see the homogeneous solution is pretty strong. It's oscillating at a fairly steady free amplitude. But now the growing particular solution starts to take over, and you can see the lines spreading out here. There's resonance. Okay, when you drive an undamped oscillator at its natural frequency, like pushing someone every time they come back in the swing with no friction, they eventually go over the top, right? Here's the case that's near this. Suppose you have no damping and driving, and the driving force isn't quite the natural frequency. Instead of being 2T, it's 2.25 T in this case. Well, now what you get is something that starts to try and resonate, but it's really just a sum of sine waves like this one, and so it cancels out. So if you think about it, this is actually really a sum of sine waves, but use the sum to product formula from trigonometry usually to rewrite it, because seen as a product, you can see that you get these beats with this frequency, this thing, the average of the particular and homogeneous solutions, and the beats equal the beat frequency equal the difference in the frequencies over two, it turns out. So you get this kind of a behavior if the driving force is real close, has angular frequency real close to that of the natural frequency of the oscillator, the mass on the spring. All right, so these three are for undamped and sinusoidally driven at a very different angular frequency, at the same angular frequency, and at a close angular frequency, right? Finally, if it's damped and driven, you just get this one case here where there's a transient solution, a sine wave times a decaying exponential, that's the homogeneous part, but the particular solution is a steady state solution. It's a sine wave that goes on forever. You're continually driving it, and eventually that just runs the oscillator at whatever frequency you're driving it. So what you get then in a damp-driven system is initially there's something from the homogeneous term here, but eventually it just settles down into what looks like a sine wave. So those are the cases you can get out of damped-driven oscillation, if you will. And all these cases apply equally well to that LRC circuit driven sinusoidally, because it's exactly the same equation with different letters. So this could be your circuit blowing up in the president's case. Now, in reality, I did try to mention last time, but it maybe real fast. In reality, there's always some resistance in the circuit, right? You don't ever get a case with no resistance like this, or a case of a mass on a spring with no friction at all. So what you get in practice is not exactly this. You always get a little bit of damping. You get the damped-driven case, but it can behave kind of like this for a little while, and there's something called practical resonance, the textbook calls it, where if you drive it at just the right frequency, even though you can't get it getting larger and larger forever because the damping starts to eventually overcome it, there is a frequency at which you can get the maximum oscillation. That's what happened in the Tacoma Narrow Bridge example. There's actually some resistance in the bridge, but it's so it's driven at its practical resonant frequency. It still generates something like this for a while. Okay, so that closes out that section then.
Going back to the homework real quick, could you walk me through number 3?
3.3.3 again?
Yeah, sorry.
Okay. Okay, let's see. This one here with the LC circuit? Okay. So now we have an LC circuit. That means you have an inductor of inductance L, and I should have given the units last time. It's Henry's is the inductance constant. So I say 1H, that means 1 Henry. L equals 1. And then you also have a capacitor on there with capacitance C, coulombs. That's for that one. And I'm sorry, farads. I'm doing the charge. Farads. So Q equals there it is, 0.01 farad. And you can put a switch on here if you want. When you close the switch, charge on the capacitors will have to switch back and forth. And we said before, what you'll get out of this, since there's no resistor, there's no damping, and this is the undamped oscillator. And since there's no applied voltage, it's undriven also. Oh, wait a minute. I'm gonna drive it with a voltage of 2.01 cosine 10.1 T. So now we're gonna look at this one, where we apply put an impressed voltage on here, they say. So V of T equals 2.01 cosine 10.1 T, 2.01 cosine 10.1 T. All right. Those seem like kind of bad numbers, but they're actually good ones. Could have picked worse ones. And initially, there's no charge on the capacitor. We're going to set up a differential equation for the electronic circuit, and we'll see it's exactly the kind of case we've been doing with the mass of the spring. Now, the general equation for the LRC circuit, where you include R, a resistor, looks like this: L d squared Q dt squared, we said last time, plus R dq dt, where Q is the charge on the capacitor, plus 1 over C Q equals 0 if there's no impressed voltage, right? The Kirchhoff's law says that the sum of the voltage drops is equal to 0. Wait a minute, it's not 0 because I'm forcing a voltage right here. When I close the gate, there's going to be a voltage here, so the sum of the voltage drops around these components has to be equal to the impressed voltage, 2.01 cosine 10.1 T. There's my differential equation. And I have to put in L is 1. Well, maybe I should put this, let's put this in next step, say F V of T, the voltage applied. And now we'll put in L. L times Q double prime plus R is 0 since there's no resistor in this circuit, times Q prime plus 1 over C. Well, 1 over 0.01 is 100. Q equals V is 2.01 cosine 10.1 T. So there's our problem here. We can just leave this out. Q double prime plus 100 Q equals that. How do we solve this? Oh, it's constant coefficients with the right-hand side found in the table of undetermined coefficients. See how nice that table is for a lot of practical problems with electronics engineering and so forth. So step 1, we solve the homogeneous problem. Q double prime plus 100 Q equals 0. But I replace the right side with 0. And since it's homogeneous, I'll put an H on here, although the book doesn't. So what's the characteristic equation? R squared plus 100 equals 0. Again, since there's no R prime term in here, you're going to get two imaginary solutions, R equals plus or minus 10I, which says that there's a general solution to the homogeneous problem, C1 cosine 10t plus C2 sine 10t. Where C1 and C2, of course, are determined by the initial conditions. What are the initial conditions on this one? This is a model, not just a general solution. We want to find a specific solution. We're also told in here that initially there's no charge on the capacitor. What does that say? And no current flowing. Initially, no charge on the capacitor says that Q is 0 equals 0, right? Q is the charge on the capacitor. No current flowing. Well, the current is the derivative, you recall, of the charge. So Q prime is the current equals 0 when T equals 0. So these are your initial conditions. The second order equation with continuous coefficients and two initial conditions at a specific time has a unique solution. So we've got a well-posed model, if you will. Everything will depend continuously upon all these coefficients and the initial conditions. All right, so this is what we've got for the homogeneous solution. Now we've got to find a particular solution. A particular solution, since the right-hand side is 2.01 cosine 10.1 T, we look for a solution of the form 2.01 cosine 10.1 T, well, not 2.01 T, gamma 0, sorry, plus delta 0 sine 10.12. So it has to oscillate at the same frequency, but it's gonna have different constants in general. And now here's where I save you a little bit of time and say, since there's no Q prime term, once again, if we have a cosine over here, we won't need the sine on this one. So we can omit this one because Q prime is not appearing and the right-hand side only has a cosine. So we'll only need a cosine here. That'll save us a little time. All right. This just comes from experience. If you're not sure, just put both of them in. You'll find the coefficient delta zero has to be zero. Right? Now, if QP, the particular solution is that, then its derivative is gamma zero times minus sine 10.1 t times gamma zero 10.1 sine 10.1 t. And the second derivative will be the derivative of that is minus 100 gamma zero sine cosine 10.1 t. Right. Now we plug these in to determine the undetermined coefficient gamma zero. Plug in to get, well, we plug it into the original difference equation. We're looking for a particular solution of this one. And so Q double prime is minus 100 gamma zero cosine 10.1 t. Plus 100 Q is plus 100 times Q is gamma zero cosine 10.1 t. So Q double prime plus 100 Q equals the right-hand side, 2.01 cosine 10.1 t. So gamma zero there exists such that this will be satisfied. That's the table of undetermined coefficients. It's a theorem that guarantees this. What do we have? We have minus 100 gamma zero. Oh, it's not 100. I'm sorry. The derivative is not 100 here. It's 10.1 squared. I should have written that one. 10.1 squared. So the derivative of sine 10.1 t is another 10.1 times this. And so this should have been not 100. But minus 10.1 squared. Now 10.1 squared, well, let's write it out. Should remember this. Actually pretty easy, right? So you take 101 and then 0, 101. Yeah, it's 102.1, of course. So this is minus 102.1 gamma zero cosine 10.1 t. All I did was square 10.1 here, plus 100 gamma zero cosine 10.1 t equals 2.01 cosine 10.1 t. Well, this is a minus 102.1 plus 100 is minus 2.01 cosine 10.1 t equals on the right a gamma zero cosine equals 2.01 cosine 10.1 t. Evidently, gamma zero is minus 1. So now you see it's a crooked problem. Those numbers actually are good. Gamma zero equals minus 1. And that tells you that a particular solution, I can draw it up here since we just have a little bit of space left we need, is minus 1 for gamma zero cosine 10.1 t. So there's a particular solution. The general solution of the associated homogeneous problem for this electronic circuit, this driven LC circuit, is this. The particular solution is this. And so the general solution is their sum. U equals C1 cosine 10t plus C2 sine 10t plus this one minus cosine 10.1t. Now, what do you think is going to happen out of this circuit? What's going to happen to it? you have this homogeneous solution with angular frequency 10. And this particular solution with angular frequency 10.1, they're almost equal. So what happens? Phenomena of beats, right? If you drive an undamped circuit near its natural frequency, you'll produce beats, just like in the video last time. So, anyway, so this will be beats. We can already see it occur. And what happens in practice is you'll get beats from a particular solution, and you'll also get a tone left over from the homogeneous solution. You'll get a sine wave plus an oscillating thing, a linearly increasing oscillation, and the sum of them is your result. Oops. Sorry, that's resonance. It goes up for a while and then it goes down, it goes up and goes down. So you get a beat and you also get a background tone from what's ever left over from the homogeneous part. So we'll look for beats in this one though. And if they're the same amplitude, then you just get beats, but if they're not, then you got something left over. All right. And so now we haven't applied the initial condition. So we'll apply to determine C1 and C2. Let's see, Q. Well, let's just put them together. Q of 0 equals 0. Q of 0 equals 0 says that 0 on the left equals C1 cosine 0 is C1 plus C2 sine 0. Sine of 0 is 0. And then minus cosine 0 is minus 1. Right? So this becomes C1 plus 0 minus 1 when you put in t equals 0 on the right equals 0 on the left because the initial charge is 0. Well, I hate to get rid of this, but I guess I've got her. All right, now you apply Q prime of 0 equals 0, that the initial current is 0. Well, you have to apply it to the derivative, so I need to compute the derivative first. Q prime, I put U, this should be Q, not U. And this should be QP, just to keep consistent with my Q's here. So QP is this and Q. And Q prime is now the derivative. This is minus 10 C1 sine 10t plus C2, 10 C2 cosine 10t is the derivative of this one, minus 10.1 sine 10.1t. So we apply Q as Q prime of 0 equals 0 to this. That means you put 0 on the left and equals minus 10 sine of 0 is 0 plus 10 cosine of 0 is 1. So it's plus 10 C2 plus 10 C2 times 1 minus 10.1 times 0. And so you get, oh, C2 equals 0. So now we know the solution to this whole thing. This is the general solution right here, somewhere. Right here, this is the general solution. When we apply Q prime of 0 equals 0, we find C2 equals 0. That's one equation. When we apply Q of 0 equals 0, we get C1 equals 1. All right, C1 equals 1. And in general, you get a system of two equations and two unknowns. Here, we're just lucky. The first one tells you C1 directly, second one C2. In general, this will say something times C1 plus something times C2 equals the number. This one also. And then you have to solve two equations, two unknowns. It's not too hard, but I made a very simple problem here. All right, so if C1 and C2 are 0 in the general solution, therefore, the final solution, how the circuit actually behaves, is that Q is equal to C1, 1 times cosine 10t, plus C2 is 0 times sine 10t, minus the particular solution, cosine 10.1t. There is the charge on the capacitor, if you like, when you run the circuit. Close the gate, if you will. Okay, well, I better get going because I got a major topic to start today. Actually, two topics, maybe. We'll see how much time we have here. The first one I had on the board when we came in, is for nonlinear second order differential equations. If you think about it, we've only been solving linear cases. We had the linear case, linear second order TEs. They were these, y double prime plus p of t, y prime plus q of t, y equals f of t, right? That's all fine, and these come up a lot in practice. The reason we spend so much time studying them is there's lots of techniques for them, right? We learned constant coefficients for important case. We learned Euler's equations. We said, well, if you can guess one solution, you can use reduction of order to find a second solution of the homogeneous problem. When there's zero here, and if there's not zero, you can use variation of parameters to find a particular solution and add and get the general solution for this kind of equation. If you can just guess one solution. And so that's, that was, a strong group of techniques. And there's a few more techniques that we didn't get into a whole lot, but now consider more generally, and these methods will apply to the linear equations, but I entitle this nonlinear because if it's linear, you really want to use one of the methods we already had usually. Now consider more generally. So these will apply to not linear and nonlinear equations. A second order equation in normal form Why do we want normal form? We have that nice existence uniqueness theorem, which we just kind of brushed over. A second order nonlinear, possibly nonlinear differential equation in normal form. That means put the highest derivative on one side by itself. So we put y double prime equals a function of t, y, and y prime. Suppose we have more generally than the linear ones we've been doing, an equation like this. Those come up plenty, right? And even if these are very important. And the reason we don't spend more time on nonlinear equations and do them more as an afterthought is simply that there aren't very many good techniques for them. A lot of times what you do is you run to the computer and get an approximate solution. You first use the existence and uniqueness theorem to say, well, there's a unique solution when I apply these two initial conditions, and I'll just run it on the computer. And that's what happens in a lot of, actual applications. You got, like if you got your aircraft is going through space and it's incurring friction. Unfortunately, friction doesn't give you, right? The air resistance doesn't give you resistance proportional velocity. Usually air resistance proportional to velocity squared for regular size objects. And so that's the way we used to usually model it at Vandenberg Air Force. We would have one of these reentry vehicles, RVs that coming down, and we'd model air resistance proportional velocity squared. Now all of a sudden it's a nonlinear equation. What are we going to do, right? And there's lots of other cases where this comes up, of course. Well, what can we do? Here's our meager list of methods. The first one is if t does not appear. If you can simplify this a little bit and say that really we can write the equation in this form, y double prime is a function of just y and y prime. What we also call an autonomous equation. This a first order. This is an autonomous equation of second order when t doesn't appear explicitly. There is a nice method for these autonomous equations. We can substitute v. Nice to think of v as velocity, right? Y is position, v is velocity. So think of v equals dy dt. But it's really just a substitution. It doesn't matter if y is really position and v is velocity. In which case, dv dt is the second derivative, right? The derivative of the derivatives, second derivative. And what we get a first order equation, right? It becomes V prime equals F. We're gonna, let's see. I put this wrong, I put the wrong one first. This should be T here. If Y does not appear, sorry, so it looks like this. This is easier to fix here than here. If Y does not appear explicitly, it's still in there, right? Because it's derivative, but it doesn't appear explicitly at least. F is written as function of T and Y prime alone, that is. Then we make the substitution and we got V prime equals F of T and V, a first order equation. And now we appeal to our multitude of first order equations to try and solve this. All right, so it reduces the order. We also had the same kind of technique if you think about it. Remember the method called reduction of order? That was for linear equations. The same kind of thing. You found a way to write it without Y in it, and so then you could reduce the order. Well, technically there's V in it for those. And similarly for second order equations, if Y doesn't appear explicitly, this will replace your original second order equation with first order that hopefully you can solve too. And so that's what our techniques will boil down to, these two. Now the second will be if T does not appear. It's almost the same thing. That's why I got these mixed up. If T is not explicitly present, explicitly appearing, then you can let the same thing, V equal dy dt. But now I just need to change this last part here. In this case, d squared y dt squared. How do I replace the second derivative? Well, that's dv dt, right? D is the first derivative. And dv dt by the chain rule is dv dy dt. Oh, wait, but dy dt is v. So this is dv dy times v. This gives you a differential equation. Let's see, y double prime I replace with dv dt, let's call it v prime. V prime times v, right? dv, no, better not write it. dv dy times v equals, I'm replacing y double prime, equals f of t and v. F of right. I need to rewrite the equation. I didn't write it down. So if t is not explicitly appearing, so that you have an equation, y double prime equals f of y and y prime. Right, if this is the equation, no t appearing, then you make the substitution, and that y double prime becomes dv dy times y. This becomes f of y, and y prime is v. So now you have a first order equation for v and y. So in either case, if t is missing or if y is missing, you can reduce the equation to first order and apply your first order techniques. And that's all we're going to do for this class. There is one more method we can talk about if you want for reducing to an energy function, which these will usually deal with those same equations anyway. But we'll just do these two for this class. These are the two that are in the notes. And so let's do an example here real quick. Find this again. Copy up here. Oops. Oh, that's where it was. Okay, so here's what we just wrote up. This is section 3.2.1. I'll give you the homework out of here at the end. This is an interesting example here. I talked about friction. Here's friction of something sliding on a table is proportional to the normal force. The weight, you will, of the object on the table. So before we had a mass on a spring that could slide back and forth like an air hockey table model without friction or something. But if there's actually friction, what's the motion? You can apply this method to solve it and find out the solution here. It's written up in the notes. I think I'll skip it because it's kind of long. You can find out what the solution is. Let's look at this one here, which is a little easier and more illustrative, I think. But I just wanted to point out that one is sort of an important problem. Right? With sliding friction, how is it modeled? Well, you can use this method to reduce the order. How about this one? Suppose I have d squared y dt squared times dy dt equals 1 together with these two initial conditions. Solve this initial value problem, right? So let's try this one. Solve the differential equation. D squared y dt squared times dy dt. So this is non-linear. It's got a second derivative times the first, right? It can't be written in that special form to be linear. Equals 1, together with initial conditions, y of 0 is 3, and y prime of 0, or dy dt of 0, is 2. What is the solution to this thing? Well, I noticed that t isn't explicitly appearing, right? Y prime appears, and y double prime appears, but t doesn't appear. That's this case here, right? So by method 2, we can make the substitution. Both of them substitute v equals dy dt. The difference is that if you have t not appearing, you then say, well, y double prime can be replaced with dv dy times v. So v dy times v replaces d squared y dt squared to get an equivalent differential equation. Well, the second derivative is replaced by dv dy times v. The first derivative is replaced by v equals 1. How about that? So we get this equation, and equivalently this is, oh, look at this first order equation is, if I put it in normal form, dv dy equals 1 over v squared. Can we solve that one? It's not linear because v is squared, but it is separable, right? I can now multiply both sides by v, so this turns out to be a separable equation. I'll apply my first order method technique for separable equations, and I'll say v squared dv equals dy by separating variables. Now I'll throw an integral sign on there and say this one is v cubed over 3 equals y plus a constant, from which we can solve for v. And say equivalently, v equals cube root of 3y plus 3c. Right? So there's the and then now that's the first order equation. Now I have to be able to integrate this, right? Because actually v is equal to dy dt by our substitution. So one trouble with this method is after you get this first order equation and solve it, you just have an equation for the derivative of the original variable. You're gonna have to integrate this. Well, fortunately, this is separable again. So what happens in practice, right, is each integration gives you an arbitrary constant. You wind up with two arbitrary constants, just like we did for the linear equations. So we'll get now dy over the cube root of 3 times y plus c equals dt, and we integrate that since variables are separated. And what do we get? I wrote it in the notes, so I wouldn't have to put this all together. This is the second part here. There it is, okay, and so, you can substitute u equals 3 times y plus c in there, and you integrate this to get, with a lot of algebra, so maybe we better put dot, dot, dot. What you wind up with, integrating this and solving, maybe I should put this, is y equals plus or minus 2 square root 2 over 3 square root of t plus 1 constant cubed plus another constant. So that's what you get with if you do the integrals and solve for y. So integrate and solve for y. Don't want to spend too much time on the details. And you can see the details on the notes if you want. All right, so there's the solution to this nonlinear problem. You see, even in this very simple nonlinear problem, it's actually a difficult integral leads to, right? So these nonlinear problems are often intractable for analytic solution like this. You often run to the computer. Now, oh, and I forgot to say, if you apply the initial conditions, this is the general solution. So you apply, just like you did before, y of 0 equals 3, and y prime of 0 equals 2, and you get two equations like this. See how I didn't put them on here, I'll put them down below. And what you get is, didn't write that up. Oh, there it is, yeah. So this will determine your constants in here, right? If you put y of 0 equals 0, you get equals 3, you get 3 equals, well, if it has to equal 3, then I have to use the plus sign here. Remember, right? 2 square root 2 over 3 square root 0 plus c1 cubed plus c2, and it tells you that gives you one equation. And so here's the other trouble with these. When you plug in the initial conditions, you generally don't get a system of linear equations. You get a system of nonlinear equations for the constant c1 and c2, which can be hard to solve in addition. On the notes, I'll just say that we solved this and we got, and then you also have to apply y prime of 0 equals 2, which means you have to calculate a derivative and plug in. Plug in y prime of 0 equals 3, I think it was, right? No, I'm sorry, this was, yeah, okay, this one is 3, and this was y prime of 0 equals 2. And you get y equals what's up there? 2 square root 2 times t plus 2 cubed. Just copying this down here, plus 1 all over 3. All right, so here's what you get when you plug in the initial conditions. They determine the constants, but you get a system of nonlinear equations, nonlinear algebraic equations now, which can also be hard to solve. Now you see why we spend so much time on linear equations, right? We actually solve them sometimes. This is such a simple equation, right? Now, the other way we can do this is to say, well, the other method actually applies. Again, if we got d squared, so similarly, the same equation, d squared y dt squared times dy dt equals 1. How simple for a nonlinear equation, right? Since t is not explicitly present. C doesn't appear except that it's a derivative. We can also use method 1. So this one, either one of our two methods applies. And so we substitute phi equals dy dt, but this time we also substitute dv dt equals d squared y dt squared. And so what do we get here? Well, d squared y dt squared gets replaced with dv dt. dy dt gets replaced with v, and we get this equals 1, a little easier equation, right? Now we separate variables again, so we get a first order equation by the substitution. Then we'll, and by the way, the textbook, I can't find any place where they really talk about these nonlinear d. That's why I tell you it's not all that important, these methods, but these are the few that people apply is reducing the order by a clever substitution. So if we separate variables, we get equivalently v dv equals dt. Since variables are separated, we integrate and we get v squared over 2 equals t plus a constant. Evidently, v equals plus or minus the square root of twice t plus c. Oh, but wait a minute, now v is dy dt, so we've got to solve the second differential equation. And again, we'll get two integrations, we'll give you two arbitrary constants that will be determined by the initial conditions. So now this is dy dt equals plus or minus the square root, and we'll choose plus here because the initial conditions force the plus sign on there. Initial condition, I think, forced the plus sign. And I stopped carrying that plus or minus. But if depending on the initial conditions, you might want the minus instead. All right, so it's plus the square root of twice t plus c. And now I have to solve this one. Well, I can. This one is nice because the right side depends only on t, right? How do we solve it when the right side only depends on t? It's our first method of the semester. We just integrate, right? So, right, if you just integrate, and you get y. There's no y on the right, you just integrate it. So it is this, y is the integral of this, square root of twice t plus c dt. Well, this is easy. You substitute u equals twice t plus c. And what do we get? The same thing as before, but y equals 2 square root 2 over 3 square root t plus 2 cubed t plus I put in the initial condition already. This is kind of a useful point. You can actually put in the initial condition early when you're doing two integrations. If I got v equals this, and I also know from the initial condition that v of 0 equals 3, right? Right prime initially equals 3, that determines this constant. Tells me, so I can determine that, plug it in initially a v here and get v equals plus the square root of twice t plus c1. Apparently it determines that c2 equals 0. This is c1 and c2. There was two arbitrary constants. And also, the initial condition v of 0 equals 3 determines that c1, c2 equals 0. If you put in 0 here, see how that works. Oh, it's equal 2. V of 0 equals 2. Says that 2 equals this. Oh, yeah, so 2 equals this, says that c equals 0. And c equals 2, yeah. But 2 times 2, square root is 2, yeah. Okay, so that's, we have this for v, and then we apply v of 0 equals 2 was the initial condition. That says that 2 equals the square root, and that tells you after you choose the plus sign of twice 0 plus c1. Well, in order for this square root to equal 2, that says c1 equals 0. Yeah, there's no c2 here because this is just one integration. Right. That says c1 equals 2, and now that means that v is this. with 2 for this, then there's a plus, and then now when you integrate this, you get this plus C2 from the second integration. And so there's the solution for y finally, and now you apply y of 0 equals 3. And the nonlinear equation 3 equals 2 square root of 2 over 3, square root of 0 plus 2 cubed plus C2, which tells you that C2 has to be a third. So this comes out to be 2/3 apparently, so C2 equals a third. And now you've got the final solution, it's an initial value problem. And this brings out, with that simple problem, all the stops here, what, y equals 2 square root of twice t plus 2 cubed all over 3 plus 1, same thing that we had before. So here's your 1/3 on the end and for C2. The rest of it here. All right, so they're solving nonlinear equations. Well, have you try some of those, how about? I think this is 3.2.1. I better check this section here. Yeah. Try this for homework. It's 3.2.1. Number 1, on nonlinear differential equations, all the problems that there consist of, oh, t is missing. I'll substitute dy dt equals v, and d squared y t squared is v prime, and then, oh, y is missing, I'll make the other substitution, right? Second derivative is v dv dy, and first derivative is v. So every problem is just make one of those 2 substitutions we did here and solve these nonlinear equations. But as you can see, there can be some awkward integrations along the way. I have some more here, but I don't think we've gotten any of these. Yeah, let's not do any of these. Okay, and I don't have any out of the text this time. This is out of the notes because, like I said, the text doesn't really look at the nonlinear equations just because they're, as you can see, not often useful, but I want you to have some sort of techniques from that. All right, so let's end that third today then. I'll be a few minutes from yesterday. And I don't want to start with Laplace transforms today because I'll do 5 minutes and then I'll have to repeat it again tomorrow with it back up to speed. So if you want to read ahead, read the section on Laplace transforms. In the textbooks, we're switching up to chapter 6. That's one of the things we always try to cover here because the engineers and the physicists to come out of here need Laplace transforms more than what they need in chapters 3, 4, and 5 of the text that precede it. So we'll do that next. I think you'll like that as a sometimes simpler method for solving some of these.